Hi everyone, my name is Chang Liu from Osaka University, Japan, and today I'm going to present our work on exploring the eye gaze-based object rotation for head-mounted displays. So as most of you may know, a head-mounted display, or an HMD, is a wearable device available for providing virtual reality, the VR, augmented reality, AR, and mixed reality, MR experience. Nowadays, we have various types of commercial HMDs, and based on how to display the virtual content, an HMD can be categorized as an immersive HMD, for example, the HTC Vive, or an optical see-through HMD, such as the Microsoft HoloLens. So the focus of this work is on how to make interaction with HMDs. There exist several popular interaction methods for HMDs. For example, for most immersive HMDs, such as the HTC Vive or the Oculus Rift, the user can use a pair of motion controllers for interacting with the content. And the controller works as an extension of the user's arm or hand, and there are several buttons on the controller for making further interactions. Besides the controllers, the gesture is also a famous interaction method. In this case, users have to learn and perform specific hand or body gestures to trigger different commands. So the voice is also used for some HMDs. For example, the user can talk to the Microsoft HoloLens to launch specific applications or just to turn off the power. These popular methods are available, but for some practical use cases, they are not efficient enough, which is the main problem this work is targeting. For example, if the users are holding stuffs with their hands, it will be difficult for them to use the controllers or to perform the hand gestures. Also, sometimes using gestures or voice may disturb other people at the same space. And more generally, some users may find it kind of embarrassing to perform gestures or talk to the device on public occasions. So to solve this problem, it is necessary to explore human HMD interaction methods that are hands-free and unnoticeable to other people. So the hands-free interaction would allow the user to interact with the HMD while doing other tasks that constantly occupy their hands. It will also make it available for the contactless use cases. For example, some users may not want to touch the public shared device. Also, the method should not make the user disturb other people and should not make the user feel embarrassed to using a public space. To achieve this goal, this work focuses on the eye tracking technology. From the eye tracking, we can acquire various information available for the user interface design. For example, we can track the pupil response to evaluate the light adaptation or the motion state of the user. We can also track the user's eye gaze position to estimate what the user is looking at and what the user is interested in. The eye gaze-based interfaces serve in a hands-free manner, and it is very easy to integrate, as the recent HMDs have their integrated eye trackers inside, for example, the HTC Vive Pro Eye or the Microsoft HoloLens 2. However, there still lacks efficient eye gaze-based interaction methods targeting the head-mounted displays. So as a step towards hands-free interaction, this work mainly works on the development and evaluation of novel eye gaze-based manipulation methods. In this work, we implement and evaluate 3 different methods for achieving eye gaze-based rotation, which are called RotBar, RotPlane, and RotBall. And I'm going to introduce them one by one. So the first one, the RotBar, is a per-axis rotation method. Here, the user needs to firstly select a specific direction to rotate. And for each direction, a bar is rendered to map a rotation of 360 degrees. And the center of the bar represents the original orientation of the object when the rotation is activated. For example, if the user looks at the very edge of the bar, he or she will get a 180-degree rotation in that direction. So basically, it's a two-step method. Firstly, the user chooses a direction axis, a rotation axis, and then rotate the object based on the axis. The second method is the RotPlane, and the RotPlane is also a per-axis rotation method. After selecting the rotation direction, the user will get a plane for performing the rotation. And the white bar on each plane represents the original orientation, and the rotation is acquired based on the angular offset from the white bar. And the last one, the third method, we call it RotBall, which is a combination of a traditional arcball with a ring around the arcball. So the RotBall is able to provide arbitrary rotation based on the gaze trajectory on the ball. The user can first set a point on a random position on the ball and draw an arc trajectory based on the first point, like this. So the rotation is calculated as an angle composed of the center of the ball and the arc trajectory. The ring surrounding the arc ball is aimed to handle the user perspective rolling rotation, as it is difficult to draw the trajectory at the very edge of the ball, like this rotation. So to evaluate the three methods, we conducted a user study. In the user study, we decided to allow the participants to use the controller buttons for selections because this work is rather focusing on how the eye gaze will perform with the rotation itself without the influence of the selection method. If we ask the participants to make selection with their eye gaze, the result of the selection will influence the rotation method, which is not ideal in our case. So basically, the participants were using their eye gaze to interact with each method and rotate the cube, and use the controller button to fix a rotation and complete each trial. Also, during the study, we did not restrict the participants' head movements in order to provide them with a natural accessibility to use their eye gaze. And in a VR environment, there were two cubes at exactly the same position with different orientation. So the task was to rotate the pink-colored cube to match the other one. And for each method, there were 8 trials in total. 6 of them were with single-axis orientation tasks, which are quite simple. And the user just needed to choose the right direction and rotate. And 2 of them were with the multi-axis trials. There were no time limit set for each trial, and we asked the participants to match the 2 cubes as accurately as possible. And when they thought the matching was good enough, they could confirm the trial by pressing the controller button. We recorded the completion time and the misalignment data for the quantitative evaluation, and there was also a system usability score survey conducted for the qualitative evaluation. So this slide shows the completion time and the misalignment results. And sorry, I'm going to hide my head. We can see that the same trend for both results. For the single-axis tasks, both per-axis methods, the RotBar and the RotPlane, outperformed the RotBar here and here significantly. And there was no significant difference between the RotBar and the RotPlane, these two. And for multi-axis tasks, we had a completely opposite result where the RotBall outperformed the RotBar and the RotPlane, both the per-axis methods. And the next slide shows the results of the SUS survey, which is the qualitative result of the study. So a system usability score here is calculated based on the survey, and we can see that there was no significant difference observed among all the three methods. Here is the brief discussion of this work. From the quantitative results, we can say that all the three methods are suitable for providing eye gaze-based rotation. And considering that there was no significant difference observed for the preference, it is recommended to use a combination of different types of methods during the practical object orientation tasks. For example, using the RotBall for complex tasks and using the per-axis method for smaller or just single-axis rotation tasks. So to summarize in general, this work takes a step towards the hands-free human HMD interaction by evaluating novel eye gaze-based object rotation methods. There is still various work left in this domain. For example, we did not add any hint to visualize the scale unit of the rotation, which definitely needs further investigation. And there also lacks evaluation on unified hands-free interaction frameworks where the users can manipulate the position, the rotation, and the scale of the virtual object at the same time in a completely hands-free manner. So we believe that the eye gaze tracking will play an important role in achieving the hands-free human HMD interaction. And we hope that this work could contribute to the design of future interfaces. And that was all of my presentation, and thank you for your attention.